What if I told you your cryptocurrency wallet, your encrypted messages, and billions of dollars online are protected just by drawing a line or curve, and no giant supercomputers or not any kind of complicated passwords? Okay, it's just really a geometry, and somehow this weird looking curve became one of the strongest security system human has ever built. And today we'll show you the beautiful mathematics behind the elliptic curve cryptography, which I was talking on previous videos. We refer it as ECC, the same system used by Bitcoin, Ethereum, and modern digital security. Most of the crypto system just feels like magic, right? You type a password and suddenly your data becomes unreadable. But ECC is kind of different because underneath all the things you see is surprisingly visual mathematics and nothing more than that. You can literally draw the operations hand by hand. And once you understand this geometry trick, you'll understand why reversing the hash value is nearly impossible in case of crypto systems or simply hashing. Now, whatever we are going to learn today, it all starts with this equation, that is y square equals to x cube plus x plus b. And this equation is called Weierstrass Equation. Now, for whatever I just said right now, the name of this equation kind of feel overwhelming, but we are just going to look at very surface level of this equation. And the thing that matters most is this graph, okay, that we get after plotting this equation. If you observe carefully into this graph, I have drawn some points here, okay. Those are points A, B, C, D, and then E. So to know the mechanism of the elliptic curve cryptography, we are going to perform addition over this point. And this addition doesn't feel normal, okay. Normally we do addition 1 plus 1 equals to 2 in this way, okay. But while adding these all points, it's going to feel different from the normal addition that we usually do. And the kind of addition that I'm talking about is the point addition, okay? And now let's see how point addition actually works. Now let's imagine 2 points on this curve, okay? The first one is point P, the other one is point Q. So the first thing that we gotta do is draw a straight line through these points, okay? The point P and then Q. So now let's draw a straight line through these points. And after drawing a straight line through these points, we get the third point, which is the intersecting point. The intersection occurs between the line we draw and the curve we had earlier, right? And so this intersected point is our helper point. Okay, so this intersected point right here is our helper point. Now there are two things to consider right here, okay? This black straight line, the horizontal line is called x-axis, and the vertical line is called y-axis, okay? So now we gotta reflect this helper point or the point of intersection across the x-axis, okay, this horizontal axis. And after doing that, we get the reflected point somewhere right here on this curve, okay? And we point this out like that. And now let's denote this reflected point with the letter R, okay? And now congratulations, we have got our result of addition, that is point P plus point Q equals to point R. So the result of point P and then point Q is the reflected point R. And this is what point addition is all about. During the explanation of this point addition, we have taken the different point P and then point Q, okay? But what if we want to add the same point? For example, point P plus point P to itself. Now for that, we have to learn the another concept named point doubling. So let's jump into the point doubling. Now before we continue, there are two tiny geometry ideas you need to know. The first one is secant line and the other one is tangent line. So a secant line is simple. Think of it like drawing a line between two dots on the curve. So two dots are this and this, alright? Now a tangent line is kind of different. It is a kind of line that only touches the curve at one point, okay? So it's like the line is kissing the curve at a single moment. And if you slowly move the two secant points closer together, for example, these are two secant points right here. If you slowly move these 2 points closer and closer with each other in this direction, they will hit somewhere like here after some time. And if you draw a line like this, and again if you continue this process, they will meet each other somewhere here. And if you draw again like this, you will get something like a tangent line. So if you move two secant line closer and closer with each other, eventually you will get a tangent line, okay? So keep this in mind. So now as the tangent line makes sense, point doubling becomes much more easier to understand. Remember, for a normal point addition, we use the secant line because we are two different points, okay, P and Q. But now both points are at the same point, okay, because we are not doing P plus Q at this point. We are doing P plus P. We are adding P to itself. And that what is point doubling? We use the tangent line at P. Instead of using the secant line like this, we use a tangent line. Remember, at this point, there are 2 points, P and P itself, okay, because we are doing point doubling. We are adding P to itself. Now let's introduce a tangent line like this. So we get the intersected point right here. So we reflect this intersected point across x-axis. At the end, we got our final answer. And our final answer is this point right here, the reflected point, okay? So now we have successfully added a point P to itself using a tangent line, using a simple arithmetic, that is point P plus point P, that is point 2P, and by using a foundational logic right here, that is point P plus point Q is equals to point R, this point P plus point P equals to point 2P. So we can easily name this point as 2P. So that was that easy. So visually, point doubling is just toss the curve with a tangent line, find the next intersection, flip across the x-axis, and done. You have got your final answer. And computers repeat this operation again and again and again and again to generate gigantic cryptographic keys, and that's the mathematical engine behind ECC. Now we shouldn't be stopping right here at this point. We should again pass a new tangent line through this point 2P. Okay, so if we do that, we again get a new intersecting point right here. Again, reflect this point across x-axis, okay, as we did earlier, right here. Now this reflected point right here is 4P, okay, because if this is P and it adds to itself and give us 2P, and here we have 2P and it adds to itself, that is 2P, and we get 4P right here, okay. And this process continues for several times. It could be a million or billion times. So that's why the cryptography is so complex in itself, okay. And the repetition is what makes it complex to reverse the cycle in the cryptography. Now after all those repeated point doubling, like P to 2P, and then 2P to 4P, 4 to A, and then A to 16, up to KP, okay. The question right here is, what does this KP really depict? So KP itself is a public key, okay. KP itself is considered as public key, and K here is considered as private key. So private key is the number of jumps, which is denoted by K, and public key is the final position after all the jumps, okay, which is KP. Now let's align this concept with the real world scenario. So here it is written that if you know K, computing the public key is easy. That means if you know private key, that is K, we just knew here, right? At this point, that is K is private key. So if we know private key, computing the public key is easy, right? So if we know K, computing KP is easy. So you start from point P as we did earlier, and then repeat that operation. That means repeat the elliptic curve operation K times. We also have already seen about this. And at the end, you get your final point, that is KP, right? So if we know private key, computing the public key is easy. Now in case of backward direction, let's flip the scenario a bit. Let's assume that you have given a public key, okay, that is KP, which is also a last point on your curve, and you have also given P, which is the generator or initial point, and you have to find K. Now at the first look, finding K seems simple, okay, so it just feels like a normal mathematical solution, alright. So this is not a normal multiplication, by the way. And in normal math, as you do 10K equals to 100, and then K equals to 100 by 10, and you get 10, right? So you could have done this, but you can't in this case, because KP right here is not any kind of number, okay. It is a point or a final point produced by a repeated geometric operations on the curve, as we did earlier. Now what you are forced to do instead is, first of all, try K equals to 1, okay, and then compute 1P, and again try K equals to 2, and then you get 2P, and then try K equals to 3, and then compute 3P, and so on until you match your KP, okay. And this is also called a brute force search. But why that fails in real life, okay? In real system, K is enormous, okay? We are talking about values like 2 to the power 256, which is very huge. So that's so large that even fastest supercomputers in the world cannot try enough possibilities, before the universe runs out. So the core idea is, you can use your private key to generate public key, but you can't go backwards. Like, you can't generate your private key using your public key that easy, because going forward is a well-defined geometric process, as we see earlier, but going backward is just guessing billion upon billion of possibilities with no pattern to guide you, and that's exactly what makes ECC so secure. And to help you understand this more visually, I actually built an interactive HTML visualization for this. So in the animation, you can literally watch Q sliding toward P, the second line rotating and naturally becoming a tangent line, as we discussed in the video. So instead of memorizing formulas, you can actually see why point doubling works. I highly recommend checking out the visualization and playing it with yourself, okay, because once you see the transition happen interactively, the whole concept clicks instantly. Now that we understand the mathematics behind the elliptic curve cryptography, let's now actually demonstrate ECC in the real world. In just few lines of Python code, we can generate the same kind of cryptographic keys used by Bitcoin, Ethereum, and modern secure systems. Alright, so we first create the private key and then we'll generate public key using that private key. Okay, now let's do it. So we are going to import some tools right here that are signing key and then SecP256K1. So the signing key is used to create a private key first of all, and this SecP256K1 is the exact elliptic curve that we just saw in this video. So first of all, we generate the private key using the signing key and the curve. So this is the exact elliptic curve that I talked in this video, and then we derive public key using a private key, and then at the end we print the values of private key and public key. Okay, so now let's run this code. So as you can see in the output, this is the private key and the second one is our public key. Okay, these are in the hexadecimal format. So if you really enjoyed this deep dive into the mathematics behind the elliptic curve cryptography, make sure you do like, subscribe, and support this channel, because we are only scratching the surface of the modern cryptography. So in the next video, I'm going to cover the digital signatures and the topics related to it. So we will see how someone can prove ownership of wallet or their message without ever revealing their private key. Okay, and honestly, that's where the cryptography starts feeling almost magical.